Um, and here I'm here to give a basic tutorial for our QTCAD software. So without further ado, let's begin. So let's just I will just start with a brief introduction for our company. So basically, our company was founded by Professor Guo in 2008 in Montreal, Canada, and then primarily focused on molecular and quantum transport software, and then recently have also begun to develop computer-aided design of innovative materials. So we have like scientific software development and also consultancy services. So our team is basically made out of 15 employees, 8 PhDs, and so basically there are all physicists and engineers, and also we have software developers. So here you can see the office near the McGill University in Montreal, and then also we have another space in Sherbrooke in one of the East Base Quantique. So the softwares that are available by Nano academics are one called Nano Decal, which is basically a quantum electronic transport from first principle. So this basically can simulate currents based on an atomistic structure. And then we have another one called the Rescue, which is basically a large-scale DFT solver for innovative material and simulations, where you can simulate a lot more atoms. So like the applications for these two softwares could be are shown here. So like to mention a few would be the molecular transistors, nanostructures, batteries, scanning tunnel microscopy, and etc. And also the focus of this talk will be the QTCAD software, which is basically a technology computer-aided design of spin qubits in a semiconductor. So basically the basic principle of a spin qubit in semiconductors is to confine either a electron or a hole in a gated quantum dot and a semiconductor heterostructure. And then use the spin degree of freedom to implement the qubit. So like you can see like a stack here, and then it's like silicon germanium with a film of silicon. So that's the heterostructure. And you can see the gates on top. And then we can see that we can form a array or like a cloud of gas in this film. And then by applying potentials to the gates on top, we can confine electrons or holes inside the semiconductor. And then we can use these gates to manipulate single qubits, spin qubits with microwaves, or perform 2-qubit gates with exchange interactions. So the advantages of this technology is that these devices are typically nanometer sized. So this will allow for a very large number of qubits to be fit on a single chip in principle. And also it can be operated in 1 Kelvin, which is you would like 1 Kelvin, like it depends on like what reference we say is a low or high temperature, but like let's say in superconducting qubits, we would typically need like 0.01 Kelvin or 10 millikelvin. So 1 Kelvin like mentally is a lot easier to achieve than 0.01 Kelvin. So this could be seen as an advantage of spin qubits compared to other forms of qubits. And also there's a lot of technologies and semiconductors and there's a lot of manufacturing capabilities that we can use and take advantage of in developing spin qubits. So here is a simple graph that I think might be helpful for just exploring the technology computer-aided design. So in a conventional technology computer-aided design, or in brief TCAD, we will have a real device, so like industry relevant, let's say like this device from this picture, or like a CMOS, or like any transistor that you would like. And then we will have a 3D model of the same device. And we would...
Hello, sir. Sorry for disturbing. Sir, we cannot see your slide. We just see the BASP code only.
Oh, oh. You don't see my slide?
Yes, sir. We is only see the BASP code. Just like you write some code.
Oh, you see the code?
Yes.
Hold on. How about next?
Yes, now it is visible.
Oh, okay. So maybe I go through these again. Okay. I'm sorry. Is the slide visible now?
Yes, sir.
Yeah,
Okay.
now it is visible.
Okay. Yeah. Sorry. So just to go back again, here's our description of our company that I was trying to go through. And here is the softwares that we have, as I talked about before. So we have Nano, Decal, and Rescue, which are like atomistically focused softwares. And then which could be used in applications, as I mentioned here. And then we have QTCAD, which I'm going to talk about. And so this is the basic principle that I briefly mentioned. And here's the slide I was in. So yeah, so in a conventional computer-aided design, we will have a device, and then we will have a 3D model, and then we will perform classical or semi-classical physics simulations, and then we would get a performance metric, or which would be experimentally relevant, let's say an IV curve. So in a same analogy, we would have a quantum technology computer-aided design, which will have a arbitrary shape, which will be fit for spin qubits, and then we can model this design or this device, and then we need to use different principles, which would need to be capturing like the essentials of the device, like using quantum physics and other more accurate models, and then we would get different performance metrics. For example, like if you're like studying qubits, we would need probabilities of the state or other more relevant metrics. So the challenges would be that the transistors usually operate at room temperature, and then they have a many electron regime. And then quantum confinement is not a principle, is a correction in a conventional TCAD.
Mohammed, your slide is not changing. It's not changing the slide, it looks.
Oh, it's not changing. So
that is main challenges of spin qubit simulation.
Yes. Yeah, that's right. Yeah, this is the slide I'm talking about.
Okay, fine.
Okay, so this witness, do you see my cursor or no?
Yeah, we can visualize the slide, that main challenges of spin qubit simulation.
Yes. Yeah, that's the slide. Okay. Yeah, please interrupt me if there is like any screen thing, which yeah, I can fix that right away.
Cursor is not visible, but fine, we can move on.
Oh, maybe I can pointer option visible. What about now?
Negative.
Oh, okay. Sorry. I guess I will just we have to continue like this. That are operating in a conventional room temperature with electrons and quantum confinement is just a correction, and we don't have superposition or entanglement. But in spin qubits, we have it's a different condition. Basically, we will have a cryogenic temperature, which would need which poses challenges to solver convergence. And then also we have few electrons, and then also quantum confinement and superposition and entanglement are operational principles. So the benefits of our software is that we can go from a device layout to qubit performance metric, basically covering all the steps. Using a Python-based device generator to import the geometry of the gate, and then we can explore arbitrary device geometries, and then we can use QTCAD to better understand the experimental results. And then we can basically get some intuition and insight before manufacturing the device that you want to manufacture. So this is like basically gives you like more intuition of your device's behavior. So ultimately, it will reduce development costs and accelerate R&D cycles by minimizing the trial and error. So our competitive advantages is that we have, so in our solvers, which I will go through, we can also have adaptive meshing, which ensures convergence and low temperatures. And then also we have, also it's covering the second point as well. So the robust convergence of the cryogenic temperatures. And also we have quantum mechanical models that are essential to predict the spin qubit behavior. So here you can see the features of QTCAD, which I will briefly just talk about. So we have cryogenic temperature, electrostatic, and then we have the
slide is not changed. That new slide you are talking about, no?
It's the slide supposed to be overview of unique features. Do you see that?
No.
How about now?
Yeah, overview of unique feature.
Overview, yes. Yeah. It's kind of strange that it just maybe it lags a little bit, or does it just gets stuck? Okay. So
You can just tell when you move the next slide so that we can give feedback.
Okay. Yeah, thanks. So here are the features. So we have the cryogenic temperature electrostatic, which will just solve for potentials inside your device. And then we have the Schrodinger solver, which basically solves the Schrodinger equation based on effective mass or other relevant theories to give you the confining envelope functions of the electron or holes inside the device. And then we have many-body and master equation solvers for chart stability diagrams, which will be the scope of all of these solvers, which will be discussing in further details in this tutorial. I'm going to the next slide. So more advanced features will be that we have in our simulation software is we have value.
Slide needs to be switched.
Okay, so I think I might need to do something because maybe I just do this. Okay, how about now? Is it changing?
Yeah, now it is changing.
Okay, so it might be better here. Yeah. So here is a more advanced features that we support. We have valley coupling. We have quantum well physics and Rabi oscillations, which can predict Rabi frequencies and leakage from device geometry and input magnetic field gradient. And then we have a spin orbit coupling and magnetic effects and for electrons and holes. So we can see the publications here, which are done by my colleagues. And then to more features that we have tunnel coupling. This is the next slide. The tunnel coupling and exchange. So basically we can talk about, let's say we have a multi-dot structure, and then we want to compute the tunneling between the two. And then we want to see the effects between the gate potentials and the tunnel values, the tunnel splitting values, and we can have those simulations. And then we have a more complicated non-equilibrium green function simulation, which will just account for conductance and current throughout the device. And also additional features would be that we have parasitic volume and surface charges and point charge defects, lever arm matrix solver, strain solver, and also we have supports for Jupyter notebooks and many more features that we will introduce. So next slide. So the use case of QTCAD, basically we have a series of publications, which if you're interested, you can check them out. And also we have scientific papers that are independently written by our users. And then we have partner R&D and beta testing partners as listed to the top right. And then also we have commercial users from industry and academia since mid-2023. Next slide. So here's the general workflow. So we will start with a device with the specifications of the device. And then, so basically the geometry and the shape and dimensions. And we will go and use a meshing models to mesh the device. And then we will use QTCAD with its flexible Python API to simulate the device, and then we can visualize it with some built-in plot features and also other independent softwares like ParaView. Next slide. So here's the workflow for the meshing part. So we will have a GDS text file from the K-layout, and then we will use a device gen software, which is open source, and then we can create a mesh or mesh files like which we support, and then we can import these files into QTCAD. Generally, if you have a more arbitrary shape, this can also be simulated. Any 3D arbitrary shape or 2D or 1D can be simulated. So in that case, even if you don't want to follow the K-layout workflow that I will go through today, you can also just use the Gmesh API or scripting languages or the Python API to create your own geometry, any arbitrary shape, and then you can import them into QTCAD. And then here are the examples that if you go to our, I'm afraid to click on them now because I think it might, maybe I just, do you see this?
Yes.
Yeah, okay. Great. So if I do this, yeah. So you can see we have other tutorials. So this is like another shape available on our website. And then we have this tutorial, which is somewhat a modified version, but similar to what I'm going to go through today. And then we have other geometries, and you can essentially build your own geometry if you want to do any other simulations. Okay, so how can I minimize this? Let's do this. Okay. So next slide. So here's the geometry of the device or the mask layer that we can obtain from K-layout. So the device, as you can see, it has, it's a box. It has 5 gates, which we name plunger gate 1 and 2, and then left barrier gate 1, right barrier gate 1, etc. So, so in principle, we would, if we have this device, we would expect the dot to be forming in the middle, and then these, so the 2D electron gas will be somewhere like along this plane in the film layer, and we will have these barriers to basically isolate a single electrons from the two-dimensional electron gas, and then we can use the plunger gate to tweak the energy of the quantum dot. So these distances are in microns, and yeah. So so here's a 3D structure as I was talking about. So we have some oxides on the shown in blue, and then we have the gates, which we will have on a global top gate as well, which is shown in green. And also, so we would expect the dot to form in the film, which is just shown in this black layer right here. So somewhere in the middle, but somewhere in this region here, which I don't know if you can see, but this is a little rectangle box that I'm pointing at, and the black layer. Here is the breakdown of the heterostructure. So we will have an oxide gate, and then we will have, which will be 5 nanometers on the top and a 5 nanometers buffer between the gates and the silicon channel. We will have a silicon channel, which is 10 nanometers in thickness, and then we will have buried oxide, which will be below the film. As you can see that we would expect the envelope function of the dot to penetrate the oxides around the edges. So if you look at the interface between the film and the buried oxide, you see that we use a little bit of a finer mesh to correctly capture this behavior. Yeah, so now we can I can show you the code and then just go through how to get this geometry. So with that, I think need to do some. Oh, okay. Maybe I just. Do you see the code or not? Yes. I think it should be visible, but please confirm if it is.
It is visible, sir.
Okay, thank you. Yeah. So we have this script. So the essential for the script to be executable is we have a layout, which I've shown in the slide, and it will be a GDS format, and we need to import or export it into a text. So this can be done within KLayout. So we will start by importing the device generator from our device gen library, and then we also import this path library to be can access these files. So here I'm just doing some quick directory management to get access to these files. As you can see, I have them in the layout folder. And then here I have this value, which I say the mesh characteristic length, which basically determines the size of each little triangle inside the mesh. So you can see that I assigned it basically to be 10 microns for the entire device, and then for the region, which will be expect the dot to form, I just half that, so 5 microns for the dot region. So basically here are the values of the thickness that we talked in the heterostructure stack. So we have the top layer thickness, we have the gate oxide, and then so this is like this is that barrier that I said that we need to. It's still in the oxide layer, but I select this to be having a little bit of a finer mesh, and then we have the film thickness, and then we have the buried oxide below it. And here are the number of points along the z-axis. So maybe I can just go back here. So you can see, I think you can see my screen. If you can't see it, I changed the slides. Let me know if it didn't change or not. But yeah, so you can see that the number of points along the z direction can be adjusted. So those values, you see like there's 10 points along this line here. So we have like a surfaces that are meshed, and then we have like points along the z, and then they're all like interly, like completely connected throughout the whole 3D geometry. So those values basically effectively change the number of points, like the number of layers or points along the z-axis. So I'm changing back to the code. Hopefully you can see that. So here are the points that we have along the z-axis. So with that, we just instantiate a device generator. We input the path to the layout text, which will be the KLayout text output. So you can see the device generator on line 34 will take the text file. It will have an output file, which will just create a geometry file, which we can use later. And then we have the characteristic length to create the mesh. So here I can just run this code and just show you, like I can just view the device and see what it is. So do you see this? This is a new screen now. Yes? No? Can you guys please confirm if you see this, my screen?
Yes, sir.
Yeah.
Okay, yeah, thank you. Yeah, so you see I have now the stack, the K layout output. So it's just the 2D output, which is typical because they're just some mask layers so it's a typical K layout output would be a 2D structure. So I can just I have all of this imported correctly. So if I go back to the code, which hopefully is shown, I need to set up a region inside this layer, as I call the dot region. So we expect the dot to be formed there. So like this is like basically assigned to the user. So like we will have a educated guess of where the dot will form, and then we will we only solve like the Schrodinger equation inside that region. So like with like some guesswork or some intuition of where we would expect the dots to form, we can create this. So I just create a rectangle with a new dot rectangle, and then you just give the minimum and maximum values, minimum edges of the rectangle in nanometers, in microns, and also I will give it the length along the x and y axes, and I also give it a different characteristic length. So if I close this, so you can see that there's a box created in the middle. And so this is basically, we will solve the Schrodinger equation inside this box. So this is just our educated guess of where the dot will form. So it's still a 2D structure. I just added a rectangle in the middle. So here, if I go inside the GMesh, I can show you that each surface inside GMesh has a name. So I can just go physical name. So you see that if I define a surface, each surface will just have a assigned or designated name using our device generator. So we can just relabel these surf names. So here you can see just surf 1, surf 2, etc. So what we can do is that to have a sort of like keeping track of which surface is what for our gates later, we can just rename them. So if I move to the code, you can see that I can just relabel surface to left layer, left barrier gate. So just simple relabeling values from using this relabel surface. So if I close this, yeah, you can see now that everything is correctly relabeled. So we have the left barrier gate, plunger gates, right barrier gates, and then we have this 2 other surfaces we will relabel later. So with the next, can just, with this command called new layer, we can just input the thickness that we want, and then we can just say how many points along the y-axis that we want. So this is basically an extrusion. We will extrude this 2D structure along the z-axis. I think it's covered here. Yeah. So you can see here, there's X, Y, and Z. So along Z, we can just extrude this 2D geometry to give it the 3rd dimension. And then we can just add the points for the meshing to be done along the Z-axis. So here, you can see that I specify the thickness, which is just a value. It's like 5 microns minus 2 microns, because I need that finer region. I specify the points, and I have a name for that volume, which is called a label. So I can repeat that that step one more time, you will have another thickness, another points, another label. And I repeat that for all the heterostructure. So this too will just be a gate oxide layer. And this line 64 will generate the film. And then the line 66 and through 69 will perform the buried oxide below. So changing back to the GMesh, if I close this, yeah. So you can see here that I have a 3D geometry along Z. So with all the layers specified. But this is still a geometry. There is no meshing, as you can see. But I have all the volumes configured. But I need, as you see in my simulation, I have a top gate, which is like an extrusion upward. So hopefully it's visible that 5 nanometers with a green on top. I need to extrude that upward. So that's a different command because the other commands were extruding downwards. So the new layer command, switching back to the code, the new layer command extrudes downwards, and then we have a new top layer command, which will extrude upwards. So you can also give it the thickness, the points, and then the surfaces to extrude, and also we give it a label for that layer, for that surface. So if I also execute this this command, you can see that there is a additional upward extruded layer here, which is called top gate. It's a little bit, because I'm showing multiple labels, it might be like a little bit too crowded, but you can see there's a top gate on top now. So now I have my geometry correctly struck, like I created this geometry correctly. So what I can do is that I can just use the GMesh software to just mesh this model. So this can just be done, switching back to the code. This can be done by just device gen method called save mesh. And also you can save the geometry file later if you want to. So the mesh format will just be, so the mesh file will basically be in an MSH format, which we will create with this command. And also we have the geometry file, which basically will be switching back to the GMesh, which will be this file with all the points and lines without any mesh point inside. So if I close this, I expect to see it's running. Yeah. So you see, I have a meshed structure now. So you can see that there is like triangles on top. These are basically in 3D, they're tetrahedrons. And we have, so you can see, I don't know if it's visible, but the mesh in this box that we created is just denser than the mesh everywhere else. So we intentionally want the mesh in this region to be finer because we want to solve for the quantum dots properties inside this region. So yeah, that's basically the device gate simulation step. So if you have any questions, I can go through them. If not, we can. Yeah, I'm gonna say like let's talk. We can talk about some questions. If not, I can go through the next steps of the simulation. So if I yeah, any questions so far?
Participants can also write their query in chat box. So Mohammed, you can also parallelly check the chat box as well.
Okay. Maybe here. Okay. Yes. So if there's no questions, we can move forward. But anytime, yeah, you can just write in the chat or in checkbook or just interrupt me. But yeah, so here is the mesh structure that we will start a simulation with. So you can see, maybe I can just make it visually a little bit better. Can do this also. Yeah. So you can see that we have this silicon layer in the middle, and then we have oxides. Maybe zoom in. Yeah, we have the silicon layer here. We have oxides below, and then we have oxides above. And then we have these surfaces that we will apply the potential. And also we have this top global surface with a different potential value. So with that, I go back to the slides. Hopefully this is visible if I'm not missing anything. Okay, so you guys can see the slide? Yeah. Yeah, please stop me if you don't see it. So basically, we will start with a basic electrostatic simulation example. And the theory is that we will solve the nonlinear Poisson equation, which is shown in this, shown here. The equation is, effectively can solve for phi, which will be the potential throughout the device. So you will have Q, which is the electron charge. You have P, the positive charge, or like the holes density, and you have the N, which will be the electron density, and then you have N plus and N minus, which will be the positive dopant and negative dopant densities. So you will have this density times Q equals epsilon, and epsilon is just the permittivity of the material, and then you can solve phi for this entire device. So the step that is, so the reason that we call this a nonlinear Poisson equation is that these N's and P's also in general are related to the Fermi level and the conduction band edge. So N is related to Fermi level and conduction band edge, and P is also related to valence band edge and Fermi level. And so these are also effectively, these values also relate to phi. So in that case, because we account for that, it's a nonlinear equation. So the way that we do is that we start with some initial guess for P and N, and then we solve phi, and then we calculate N and P, and then we put them back in, and we solve this step iteratively to obtain a phi below a convergence level. So once we find the phi, accounting for all the gates and biases, and once we obtain the potential inside the device, we can solve the Schrodinger equation. So the Schrodinger equation, hopefully this is visible. Basically, we will just find the envelope function, which is called the FR, for the effective mass single valley. We can check these references for further details. But basically, effective mass is just that we model the electrons inertia with different values along different directions. So like the mass will just basically be a tensor for the electron. So we can find this is effectively an eigenvalue problem. And then we will have this FR, which will be the envelope function throughout this quantum dot region that we specified. And then we can find E, which will basically be the energy of the orbitals. So you can see that if I make a cut along this red line, you will see the dot region in the middle that we specified by creating that rectangle. So inside this box here, that's where I will solve this Schrodinger equation. So there are a lot of discussion and a lot of literature around convergence of the nonlinear Poisson as challenging at small temperatures, and also the adaptive meshing should be used to ensure that things converge, which is a paper done by our colleagues. Next slide. Okay, I will jump into the code now, and here I have some backup in the case that's simulation, some issues, but hopefully we'll don't have any. So do you see the next code? Yeah. And I'll wait because this might. Please confirm if you see my screen. I've changed into.
Yes, we can see your screen.
It's
Yeah,
visible.
thanks. Okay, so here we have the second script of the tutorial. So we'll solve the Poisson and the Schrodinger equation. So we will import some dependencies. As before, we have the path. So now we go to the QTCAD. We have constants imported. We have the mesh module. We have the IO for saving. I think, yeah. Yeah, okay. Yeah, someone needed to mute themselves. Yeah, so we have the IO for saving, and then we have analysis module for plotting, material for defining the material properties, for example, the permittivity.
Sorry for disturbing. We are only see the device generation.py file, not the Poisson's and Schrodinger equation.py file.
Oh. I think this is just. How about now?
Yes, sir. It is okay.
Okay. Yes. Okay. Great. So Poisson and Schrodinger.py, that's what you see? Yeah. Okay. So we have the materials for the defining the material properties, and then we have the device, which will basically hold the geometry and all the values, all the materials together. And then we have now the Poisson solver, which will which will take a device and solve the Poisson equation with its parameters imported also, so that you can just specify what tolerances do you need, if what initial guess you want to use. If you want to use adaptive meshing, this all can be specified here. And then we also import the Schrodinger solver from the Schrodinger section with its own parameters for convergence, the number of orbitals, the number of dimensions for the number of orbitals that you want to solve. Yeah. So here I just have some gate biases. So if you remember, we had maybe I can just show you. So here we have a top gate. I think it should be visible. Yeah, I see it. We have a top gate. We have left barrier gate 1, plunger gate 1, right barrier gate 1, and it's around the underside. So I have just found some biases to some values of potential to be applied to these gate boundary conditions, as you can see them. So going back to the code, these are the values for the top gate. I just apply 0.6. For the rest, I apply 0.5. So here I just sorting the directory to the MSH file. So here's the output of the device gen script. So we'll have it in MSH. And then also we have the output path to save our files. So here we just instantiate a mesh object in QTCAD, and then we also give it scaling. So if you remember, the device gen that we created was made with microns, but so the dimensions were in microns, but here we just specify scaling factor to make sure that units are consistent, and then we also give it the path to the mesh file. So if I run the script and if I've done all of the meshing correctly, I should be able to call this line called 36 called mesh.show and should see the mesh. So let's see. Yeah. So here you can see I have the mesh correctly imported in QTCAD. And you can see the 3D geometry. And you can see, I think it might be clear here to see that there's like a denser, like a more dense section of the mesh in the middle. So with that, so we have to go and assign these volumes in the heterostructure layers, and we need to assign a correct material. So if you remember, we had for each layer we had a label for the volume, and I just assign it to the material that we have this from our material module. So we have the silicon oxide, and then we assign all the layers above the silicon the film to be silicon oxide, and then we have the film, which will be silicon, and then we have the layer below the film, which will also be silicon oxide. So in principle, we have a lot of support for other materials. For example, we can work with germanium if you're interested, and we have aluminum oxides for other like for other cases if you want to use other like materials. And we are also growing that library, so we can add more materials if that's if there is a different material that you want to use. We can also you can also create it yourself and just use it in QTCAD. And we're also adding some default materials, new default materials. And so once I've assigned every region with the appropriate material, I also define the gate. So I say, okay, here that surface inside the geometry with this. This is a gate boundary condition. So this is the tag for the surface value in the mesh, and this is the bias that I defined above. And then also there's a work function, which is basically be the mid-gap work function of silicon. So I just define my gate boundaries with all the potentials applied at those surfaces. And then here I have the dot region, which basically just specifies the region to where the Schrodinger equation should be solved. So I have the dot region, which basically just the tag for that box that we saw, and we just set the dot region. And here you can see the Poisson solver param. So basically we have the tolerance here set up, and then there's like a lot of arguments that you can modify. You can use like adaptive meshing, and you can use like number of iterations. It's typical like iterative solver parameters that can be adjusted. There's a lot of like modularity here. Also, we have the Poisson solver. So now we have the device set up, the regions and the boundaries correctly set up. And then we will have the device, and then we will pass the parameters. Then we have the solver to solve. Once the solver solves the Poisson equation for this device, we will have the output saved. And then we can also see some conduction bandage or band diagram plots along X and Y direction. So you can see X and Y are this plane, which we will expect to see confinement. So we have to, if we simulate and our simulation is done correct, and like these biases are enough, you should see the conduction bandage. We should see a confinement in the middle of the box. So I will just go back to the code. And so you can see solving Schrodinger equation in the terminal.
Sir, you have muted yourself.
Oh, does that happen now, or?
This figure, what you're explaining, you can repeat. The
Okay.
other chart was clear.
Okay. So yeah, so here you can see that the solver has converged. And for this figure, I can show you a better description. But the red is the conduction band edge, the black dots is the Fermi level, and then the blue is the valence band edge. So you can see there's a band gap, but you can see that the conduction band edge, if I zoom in here, dips below the Fermi level. So this is we expect a confinement here, right? So this is like approximately in the middle of the device. So we see that our biases were correctly set. So because we see the conduction band edge dip below the Fermi level, which is what we want for confinement. So this is for it's like along the line in the X direction. And this is another one along Y. So you can see the conduction band edge also dips below the Fermi level. So I am going to show you. So here you saw that I saved the files in the code. So I can save them using our io.save. And then I can save the conduction band edge and the N, which basically is the electron density in centimeter cubic. So I can, so I save them with a BTU file. I can go to different software, which will be here. Let's see. You should, I'm switching to a different software called ParaView. Stop me if you don't see this. So here's the conduction band edge. So you can see the 3D values of it everywhere that it was solved. I can, here, there's like a lot of modularity. I can just make a line cut along Z. Let's say, yeah, so I can just apply a line cut. If I do this, okay, wait. As long as that. And then if I rescale it, yes. So you see, I just created like a slice of it from the middle, and then you can see that this might be clear. So like the light blue is 0, the dark blue is a negative value, and the red is like positive 0.1. So you can see in the middle we have something that goes below 0, which is which we expect confinement, and then you can see that everywhere else we have like values that are not confining. So like the charge will be confined in the middle as we expect. And also I can just plot other, like the charge density, for example. You can see that the charges are accumulated like in the edges, and other properties that are our interest can also be. Going back to the code, again, stop me if you don't see it, but I'm going back to the code. So here also we saw the plots, and yeah, let this go. So you can see that we find the confinement potential from this phi, and then we create the smaller region, which we call the subdevice, to be solved using for the Schrodinger solution to be found there, to be solved there, and then we found the envelope function. So you can see also I'm just setting the tolerance and the number of the orbitals that I want. So I have the Schrodinger solver, which I pass the device, the subdevice in this case, which will be the smaller box, and then I have the solver param, which contains like the tolerances and other values of interest. So you can see I can print the energy levels for all these 10 states. So if I go to the terminal, so it says that the Schrodinger collision solve in 0.2 seconds. And then here are the energy levels of this 10 orbitals that it considered. And also we have this feature called analyze dots, which analyze dot will do is that just calculates the average of the envelope function, and you can see that we expect the geometric position of the dot to be right in the middle of XY plane, but it will be in the film channel, in the film layer, which is like 9 nanometers below the 0. And then you can see that there's standard deviation in the size of the dot, which also printed. So here also we can just have the eigenstates or the envelope functions to be saved, and we can just visualize them later, or we can just use in-house plotting to see the ground states or the first excited states. So what you saw here, this is the ground state. So you can see that the highest value is at the right at the center, but not exactly at the surface. So you can see that it's confined below in it's just basically is confined in the film layer. And so here's a ground state, and here is the first excited stage, which is just like it goes to like a minus peak value and then to a big positive peak here. So it's and then if you just continue plotting them, you can just see all the 10 eigen states, which I just shown two for in this tutorial. But like you can just, in principle, you can just do to all, like to, you can see all the eigen, the envelope functions of all the 10 states. So you see, I have also saved the file, so I can go back to ParaView. Hopefully you guys can see this. So I can just go to the Schrodinger, which is just the saved file. If I visualize it, set the scale correctly. So this is the ground state. So this is like so you see the envelope function is a 3D layer, and then I'm just showing like a transparent view. So you hopefully can see that there is like a peak in the middle. And then we have the first excited state, which a peak and a maximum and a minimum along y direction, right? So it's along y, we have a maximum and a minimum. And then if I go to the second excited state, let's say, it will be along x. So it will be a positive peak and a negative and a minimum, a negative peak here. So here will basically be the Schrodinger and Poisson workflow. If you have any questions, feel free to ask now or let me know. I'm gonna wait for a second. Oh, okay. Someone has raised their hand. Yeah, please go ahead. Open queue.
So participants have some query. Kindly, you can unmute your mic and you can ask your questions to our speaker.
Yes.
There is a chat box near this 93 number is there.
Yeah.
Near that there is chat box is there, message.
Okay. Okay, let's go. Is QTCAD full develop? Okay, so development is thank you for your question, but the development is we have these these features that I'm talking about today. They're all like completely developed, but we are still working on to add further features to it. So it will be like it's an ongoing project. So if you want to work with us, we can we are adding more features like as we go forward. So is there any relation in the mesh point and the thickness of the number of more? Okay, so this is so we in QTCAD we basically just use we don't simulate the atoms. We just like simulate the material as like a bulk material. So like the atomistic features will be later introduced, and then I will go through them. But like in these simulations that you see, we just assume a material, and each point is just like, you know, a point in the middle with like you know, an epsilon or like some macroscopic properties assigned to them. So hopefully that would be clear. Please. Okay, I think I missed this part, but hopefully things went smoothly. So if there, so I'm not exactly clear on the STT MMRAM devices, but if it fits below, if it fits with our capabilities, we can definitely like try and to see how it will work. But I'm not exactly sure what these are, what these devices are. But like if they're basic, if they're made out of silicon or like other materials that we support, or like if the behaviors that you want to see can be captured by solving the Poisson equation or other solvers that I explained, it definitely could be a possibility. We can easily calculate the induction. Okay, so I don't think we can. We don't. I don't think we have a. Okay, so I will just skip this induction part because I'm not sure if he support like calculating inductions or not. But I don't think we support like induction currently. But we can work on that and later. So, but yeah, I think which CAD. So, I mean, I'm have interest in QTCAD, so I would say QTCAD, but I guess this will be for you to decide, I guess. Tutorials or just like what I explained, or like you can go to our website, and then we have tutorials that you can go by installing and then just following these steps. Your complete descriptions here that that are here. They can follow along. Thanks. So how much time do I have? Because I still have a little bit of a slide left, but yeah, please. But we still have like half an hour left, right? Am I correct or no?
Yeah, 25 minutes.
Okay, yeah. So here, yeah, please again, like ask your questions in the chat. I will come back to, and like at the end of the session, I will respond. Oh yeah, go ahead. Yeah, unmute, and Ravi, you can unmute yourself. I think you're still muted. Oh, so for Ravi, I don't think I can hear you. Like you're still muted. So for this, all of these dependencies, if you install the QTCAD, they will all be installed together. So you just need to install QTCAD, and all of these dependencies will be taken care of. So all this thing that I'm talking about comes with the whole package. So like these G meshes and everything, it's pre-installed when using QTCAD. I think you're muted. Okay. Don't know if I can unmute you. Maybe you can. I'm sorry, but can you unmute yourself or no? I guess, or you can type something. I mean, there is a learning curve, but like we have this device gen basically. So like, so if you already like, let's say if you already have your geometry, you can just like in K layout, this will be very easy. And but it just depends on like, there will be a little bit of like work to basically implement the geometry, but every like once everything has been done, like you can go forward with that. But yeah, there will be like some learning curve, of course. But that's true for every software. So like if you have other softwares, they also need, you need to define your geometry somehow. I'm sorry, Ravi, but if you can type in the chat, but I don't hear you. So I think maybe you can ask the question at the end of the session. So I'm gonna move forward. I apologize, but I'm gonna move forward with the presentation, and then we can have a question later. So in QTCAD, this is the final question. In QTCAD, we don't have any, so we can go to temperatures as low as 10 millikelvin. And then because we have adaptive meshing, this is one of our advantages, as I described. So we can converge at any temperature value. Thanks. Yeah, so we don't have any temperature limitations, so we can just refine the mesh and our algorithm works pretty well, so we can converge at any value. Okay, so going back to the simulation, going back to the presentation. So yeah, here we saw the results. So for the final part of the simulation, we will have the charge stability diagram, which basically, so imagine now I have a confined dot in figure A and B. And so if the electrochemical potentials, or like so basically this electrochemical potential as described in the top right is a number of, is the energy to add a electron to already existing n electrons, or n minus 1 electrons. So if you, let's say if you have n minus 1 electrons inside the dot, you want to add another one. So we can just subtract the ground electron ground states, and then you can see that how much energy does it, how much energy lifts, how much energy is needed to add another electron. So if the energy of the, if that energy is below the energy available in the source and the drain, we can have a hopping inside the dot from the source. And then if that energy, again, is like higher than the drain, we can have the electron leave the dot. So we will have a two-step from the source into the dot and from the dot outside to the drain. And so if I just compute the current along this channel, so I have a source, a channel, and the drain. So if I just compute the current, and if I just modify these energy levels, which I can do with the applying different gate voltages, I should see peaks. I should just see like a sharp peak of a electron coming in, electron, another one, and another one. So like these peaks basically correspond to an electron coming into the device or into the dot. So you can see that in the picture C on the left. And then also I can just also change the source and drain energies. And then I can see a 2D diagram of this current. So you can see that in this diamond regions as a 1, 2, and label 1, 2, 3, 4, 5, 6. We have no current, meaning that we are in the state A, shown in the top left. But in the regions that are like green or red, we are in a we're in an open state. So like the current is flowing through the device. So as you see, if I increase the source and drain bias, I'm basically increasing. So there's a lot more opportunity for the electrons to flow through. But if the source and drain are 0, then there's a limited window for the electrons to hop in and hop out. Yeah, go ahead. Yes, yeah, I will have all the information at the end of the session. So going to the next slide. So we have I'm just talking about the workflow. So we will, for us to accurately model this system, we will need a many-body Hamiltonian. So with the many-body Hamiltonian, we have to have a Hamiltonian that has all the energy of the dots inside the channel, all the states of the dot inside the channel. And then we also have to model the reservoirs, which we'll call source and drain. And also we have to model the reservoir tunneling. So like how the source and the dot and how the dot and the drain couple together. So you can see that we're using the second quantization Hamiltonian for the many-body. And so we built this Hamiltonian based on the single electron eigen solutions. So if you remember, we had the single electron eigen solution from the Schrödinger equation in the previous section. So we can use those single electron eigenstates, and then we can build this basis set to have a many-body interaction now. And so we can diagonalize this Hamiltonian, and then we can calculate the transition rates between the many-body eigenstates using Fermi's golden rule. And then we can also, at the end, we can just solve the master equation for transport in a steady state. And then we can find the currents here, which also like P is the population of one of these orbitals. So in a steady state, the rate of the charges coming in and leaving would be constant or 0. And then so you can see that we have a plus term, and then we have the negative term and a plus term, which so in an equilibrium, we would expect the population to be stabilized with respect to time. Going to the next slide, so we can go back to the code to go through this workflow as well. So here, maybe I just do this. Please stop me if you don't see the script 3 charge stability diagram. So here we start with just importing the same as before. We have the dependencies. So the thing to note here, we have a many-body module and a master equation and a junction. So these 3 that are indifferent. So from the many-body, we construct the Hamiltonian, and then we have the junction for the whole channel and source and drain simulation, and then we have the master equation to calculate the current through the device. So here, as before, we have the gates set up, we have the mesh path to the mesh, and then we have the mesh shown. And then you see we set the temperature to 0.1 Kelvin. So like in theory, you can set it as low as you want, but you may need to allow for adaptive meshing and to ensure it converges. So, so boundaries, and then here, for speeding up the simulation, I just skip the Poisson step, and I just load the results from the script 2. But effectively, I'm going back to script 2 again. So you can just do a Poisson solve instead. But effectively, they're the same here. Here, I solve for the Schrödinger equation. And define the eigenstates. And then I construct the many-body Hamiltonian. And then I instantiate a junction. So here's the part that is different here. So we have the junction, which basically is a subdevice as before. So here we don't specify the source and drain. So the simulation assumes a sufficiently far away source and a drain from the subdevice. But in principle, you can just add your own leads or source and drain objects to this. And we have the many-body. I think we have the many-body solver param, which will just which is needed for the number of the truncation of the number of states. And so here we can, when we instantiate the junction, we can calculate the chemical potentials, and then also we can calculate the Coulomb peaks. So at the next step, we just assign a near zero source and drain bias, as can be done with set VS and set VD. And then also we use a simple broadening function. Because we didn't define the source and drain, we can just use a simple constant broadening function for the source and drain. But in principle, we have the capabilities. If you have a complicated device with its own source and drain, you can effectively simulate these values more accurately. I think I'm hearing something. Oh. Sorry, I think
इनको खाना खिलाते हो ना? Hi.
Hi. Yeah, okay, thank you. So here we have the broadening functions. So also I just have some sweep range to calculate the current. Say, let's say I want to going back to the device. Let's say I want to apply, so like you see I had like 0.5 applied to all of these orange gates. Let's say I want to just sweep from minus 0.3, from like 0.2 all the way to 0.7 for these two plunger gates to see how many electrons can I fit through in the dot. So I'm just sweeping these plunger gate 1 and plunger gate 2 from like a certain range to see how many electrons can I put in my dot. So you see I have the current setup. I'm going through the for loop. I'm setting the gate's potential, and then I'm calculating the current. So here I'm just plotting the current. And so if I run the script, you should see that result of the currents below. Okay, so yeah, close that. So yeah, so you see, so if I sweep it from 0.2, so here it has no electrons, and then at a value like say 0.35 to those two plunger gates, the first electron will hop in. So I see like a big peak. It's like 1 picoamp. So like we're talking about like 1 electron, so like picoamps is expected. And then if I continue to further increase the plunger gate biases, I will see another peak at 0.6. So here's a 1 electron region, here's a 0 electron, and here's a 2 electron region. And in principle, I can just continue sweeping and I can see more electrons inside the dot. So now I can just modify the source and drain to get a 2D behavior of like how the plunger gate variation and how the source and drain potential variation will create, how the current will look like if I start to vary 2 parameters. So that can be done with just like a double loop, with one loop changing the plunger gates and then 1 loop changing the source and drain. And then we can see that starting to calculate it. So it's 25% done. So so basically I'm just looping through the various biases. So we have to wait for it a little bit. Okay, yeah. So now we can see that at 0, I expect the same behavior because I just had a near 0 1D line. But now I see that if I change the source and drain, or the drain specifically here, I have this whole region of no electrons. And then I have this, like, so this is can be the off state and these are the on states. Or like I can have 0 electrons here, 1 electron here, and 2 electron here. So this is basically what like a lot of experimentalists are interested at, to find like working regions that you can have a quantum dot inside the device. So you have a 0 electron region, etc. And so in principle, this can be scaled to have for larger electrons, and I will go through that a little bit later in this in the presentation. So if I close that, so that would be the end of the coding part. So if I go back to the slides, so yeah. So you can see here, these are the results. And here I have on the right side, I have a 2D plot, which is a little bit nicer. We have the 0, 0, 1, 2 electrons. So I just basically use the finer points, so it's not a little bit ragged. But for demonstration purposes, I just used a little bit coarser in the code that I showed you. Going to the next slide. So the conclusions. So for this whole tutorial, we basically went through and started from the geometry that describing the experimental device and the gates, and created a realistic 3-dimensional device geometry mesh. So like all of these can be done within the device gen module. And then we now solve for the nonlinear Poisson, which describe the electrostatics as a function of this applied gates. And then we solve the Schrodinger equation to get the envelope functions of the electrons in the dot. And then we have constructed the many-body Hamiltonian and solved the master equation and in the Coulomb blockade regime, and then we obtained a charge stability diagram that's shown in the steps before. So we have commercially partners in academia and industry. So some partners to mention would be the ST Microsystems and Qubit and the National Research Council in Canada. So the future directions will basically, so this is basically would be a better answer to like what are the development stages. So the future directions are just to have defects and roughness. So to have to be simulated. So let's say that I can just simulate a point charge, like so that was created based on a defect, and then I want to see how does that change the behavior of the single qubit gates or 2 qubit gates. So this is the future direction that we have. There's already tutorials available in our website for this cases. And then also we want to scale it to larger quantum dot arrays. So this is like a picture from a recent paper. So as we want to scale the operation, we need more dots in the devices. So we showed that we have the capability to simulate few electrons, but we want to be able to scale and like do a lot more. So this basically would just be code optimization and parallelization, and other like scientific like workarounds, like using like a Fourier box to have a faster, like a different way approach of to be able to solve a many-body Hamiltonian faster. And then at another level, we have the multi-scale simulation, which will basically be the integration of the atomistic and the finite element solver. So in this case, we can just have the atoms and the structures basically imported, and we can have the strain physics and the surface roughness and all of this, and then we can model the devices more accurately. But these are all in the future directions that are under development currently. So here are the links, which if I share these slides at some, I think at the end of this tutorial, we have a client portal. You can maybe just, we have documentations. Yeah, so you can go through all the documentations. So here you can go to QTCAD. We have all the steps, so installation, and we have a 30-day license activation that you can use. And we have theory, which basically sufficiently describes in more details what we have available. Yeah, the Poisson, the Schrodinger, all of the all the steps that I talked about and many more. And then we have some examples, some tutorials that we have ready. You can just go to the tutorials and see like the scripts and everything is available, so you can see in much higher detail any other behavior that we have here. Also, we have so we have installations and like basically went through all of them. Also, so here thank you so much for listening. And that would be the end of the discussion. Thanks. So so I think we have some time to go through questions if there are any questions. But here are the emails for contacts if you.
Thanks for the demo. It was a really nice one. Thank you.
Thank you so much. Okay, so I will maybe. Where's my? Okay, here. I can stop sharing. Or maybe I can. Thank you so much. Okay. Okay, let's see. I can simulate texture solar cells. It just depends on what behaviors of the solar cells you want to model. Like, so if any behavior within so this is more tailored to spin qubits at this point. So I don't know if that would be needed in solar cells. So, but if there is any sort of interest in like some electrostatics or other available solvers that we have, we can try that. But this QTCAD is more tailored to spin qubit quantum computing. So I think I provided the email. I don't know if the recording is available, but we can confirm. So we can also solve the many-body Hamiltonian and confirm, which are available in the tutorials. Can you? I don't exactly know the name. And I think I've basically, okay, thank you so much. Have a good day.
Thank you, Mohammed, for giving the nice talk to our audience. And it's really appreciated to you. And we will keep in touch if any more information needed for our participants.
Yeah, sure. Yeah, I can also share the slides and the scripts with you, and you can distribute them to the audience.
Yes. You can share us your email. We will share with the participants.
Okay. Yeah.
Okay. Thank you. Thank you to all the participants for attending.
Yeah. Thank you so much. Have a good night.
Good night. Bye-bye.
Have a good day. Bye-bye. Good night.
Bye.